afternoon. We were looking at the Pascal triangle, the order group that you get from it by again, putting in copies of Z. And then if you can really, you could actually give a whole course on battery diagram. Just talking about what the beginning of that might be. By the way, instead of Z, if you wanted to, if you weren't talking about AF algebras, you weren't talking about standard Rabi approach to AF algebras. These multiplicities, you put a Q here, the group of rational numbers, put the real line, the ordered group of real numbers. And at every place you can put that particular order group, and then you have some logical graphs, some embeddings, and the finite direct sum of copies of your basic group at every stage into the next stage. Increasing sequence of order group, increasing sequence of positive codes. And the union then would be the limit. So this is an order group, and it turns out that, well, first of all, as a group, it's pretty easy, pretty simple to see that you can think of it as the polynomials. Right? Is everyone taking a look at that? Charlie, are you okay with that? So, by the way, in the Hausdorff moment problem application, we were saying in the prescription note, yeah, we put the moments down the associate the moments to the left-hand points in every row. Okay, and what that means is it's natural to do that, and then fill out the diagram in a unique way, so that the sum of any two adjacent numbers gives you the preceding number, common preceding number. And then, well, by the way, remember the Hausdorff solution to the Hausdorff moment problem. The sequence of numbers, positive numbers, right, is the sequence of moments. In other words, integrate take the integral of x to the 0, x to the 1, x squared, and so on, over the interval 0, 1, vector measure. So the integral with respect to x, of course, x to the 0 is equal to 1. And the integral of that is, well, you might take the integral of that to 1, in which case it's not a probability, but measure the whole space with 1. Okay, so this is the interpretation of the Hausdorff moment problem. This is not a proof so much; it's just a statement. That and it's, you could also say it. You don't need to arrange things in Pascal's triangle. You can just say, look at the higher order differences, right? First order differences, because these functions are decreasing on the interval. The moments get smaller, functions getting smaller. Then they are moments of a measure. Then the difference is going to get, the difference is going to get, the difference is going to be positive and get smaller too. Okay. so what that suggests is that you should look. So now we're putting aside for a moment of it for a while. We're just looking at the ordered group, and we're noticing that it seems to be natural to ask the isomorphic to polynomials of z of x with some order structure coming from point evaluation. Okay? Considering the polynomial as function. That's, well, I don't know if anyone would guess that, okay? But that's true. Anyway, purely algebraically, if we get into an order structure, if associate these generators at the first stage in every level, in every row, first, then already you get a generating set for say the z of x, which is the monomial. Then you get monomials associated to all the other points too. And you can say that those monomials are positive. So it's monomials in x and 1 minus x. Right? So that will, as the Bradley diagram approach says, those are positive. So that's so that's the order structure of that x plus. Let's say sub p for Pascal. Okay. Pascal order relation is the positive cone is the semigroup semigroup generated by x to the n. N equals 1, n equals 0, 1, 2, okay. Semigroup generated by these elements. Well, if it's coefficients in z, coefficients in q, then you have rational, positive rational coefficients. Oh, by the way, one thing you see with this is that it has the what I would call in the Birkhoff interpolation property, Birkhoff interpolation property. For an ordered set that we have many elements bigger than, each one is bigger than each of many other elements. Separate them like this. In the special case, if there is a single element in between, well, that's called the Reese interpolation, but it's called the Birkhoff interpolation property. 42. Two papers in the end. But I think it's 42. It could be 41. And for another group, is what z of x is. The properties are equivalent. I mean, the Reese Birkhoff Reese interpolation property is equivalent to something called the Reese decomposition property. But the reason I'm mentioning that is that it means you can avoid the Weierstrass term to show that the once you've got the pointwise order on these polynomials, they're dense and continuous functions, which is getting back to the Hausdorff moment problem. You don't need to know you don't need to know the interpolation property if you're willing to quote the Weierstrass. But just mention it because once you know that the order structure, I mean, you could just say you could be looking at z x plus with respect to okay, here it's capital P stands for pointwise. That's why I'm spelling it out as full. The pointwise meaning on the strictly greater than 0 on the open interval. Okay, so that's a voided relation. Positive cone will be 0 together with the polynomials that are strictly positive on the interval from 0 to 1. So, okay. But if you find, now it turns out these are the same. These are the same positive cone. But if you don't know that, and you just look at the pointwise one, then if you might want to know, you might occur to you to ask whether or not it has interpolation problem. And you have to prove that. You have to prove that. But if you know that it is the same as the one that comes from the Bradley diagram, then it's obvious because every stage you have the interpolation property. And so for the union you do too. So, okay, so but if you want to get the solution, you want to derive the solution to the Hausdorff problem, you have to know that the talking about positive functionals on this order group. It's easy to see that those are just parameterized by the sequences that we're talking about. But you put the positive, associate positive numbers to these points, and then when you fill in the diagram, all the entries should be positive. Okay. That's what positive functionals are on this Pascal order group. Okay. And as soon as we know that that this is well, we know it's the same as the pointwise order in the open interval, and then we get extend to continuous order. It's quite an interesting proof that the two the two semigroups are the same. Two order structures on a group of polynomials and integral coefficients are exactly the same. Okay. Yes. Well, okay, so the positive cone in our group is a semigroup, right?
Yeah.
Goes under addition and contains 0. Well, so if you say look at the semigroup containing 0 and then containing these monomials. Oh, you know, I wrote it down. I'm sorry, I left some out. Is that what you were going to say?
Oh, no, I'm just wondering, is it just?
Yeah, but okay, but that's quite important. But let's go look at what you wanted to say.
Oh, I just mean like, is it like, with any polynomial with positive coefficients?
No, look, I've got, well, yes, those would be positive, okay? But I left out the other ones. I left out the 1 minus x, okay? So it's not just x to the n. It's x to the n times 1 minus x, maybe to the n minus k, okay? Where k goes from, so n is 0, 1, 2, so and then k is 0, 1, 2, up to n. Okay, so, well, no, it could be larger. It's just n, okay? All monomials in x to the n. And, yeah. Yeah, so it's a semigroup generated by 0 and x to the n, 1 minus x to the m, where n and m are equal to 0, 1, 2, 4. Okay. That's the positive tone for Pascal. Thank you for giving me a chance to notice I know those. noticing in particular that if you write it, the polynomial in the usual way in terms of powers of x, then something, that polynomial would be positive, I guess, if and only if. Well, no, it would be positive if the coefficients are positive. Okay? But there are other polynomials that are positive too. For instance, 1 minus x. The coefficients are not positive. So yeah, that's what. So it's it's an interesting order relation, even when you just look at it from very elementary algebraic. Then there's this other, talking about functions, then it's often to say, let's look at positive functions that are positive pointwise. Okay? Well, it turns out that these particular functions, they're positive pointwise. Well, that's easy to see. Put in some number between 0 and 1, you get something positive. Okay? And if it's strictly between 0 and 1, you get something strictly positive. But it's a delicate question to prove the converse. Okay, so I'd like to take a look at that because it shows off some important methods. Okay, so the question is, do you have? Is there a hand up?
Yeah. So we're including 0 in our.
Okay, I'm curious which hand was up. Sorry.
So we're including 0 in the Pascal setting.
Well, also the other one. Oh, okay. Well, sorry. Yeah, sure. I mean, 0 is always positive. Okay, in large swaths of mathematics, it's considered positive. And whereas sometimes people say positive be the sort of the opposite of non-negative, which is kind of bizarre. That only works for totally ordinary sets, right? If you look at the first quadrant, if you look at the plane, the first quadrant is positive. That's an order of vector. Well, negative then means the third quadrant, right? So what's a non-negative? It's union of 3 quadrants. Okay, but that shows that yeah, that shows that be a little careful about language and go beyond this thing.
Because
Yeah, well, thank you. Yeah.
If we don't have this, like if we have we can have a polynomial which is like say 0 and say x equals 1/2, but it's just everywhere else in the polynomial. So that wouldn't be in the Pascal setting. So
Which wouldn't be?
oh wait, no, okay, you just never mind.
Okay, well, I'm claiming these two semi-groups are the same, okay?
Right.
And it's obvious one is included in the other. And so I think it's a very good exercise, very good question to look at this from an elementary point of view and try and prove the converse without using fancy functional analysis. Yes, please.
It just seems like, just to follow the target, it seems like 0 isn't the positive code for Pascal, but not.
Oh, I just put it,
okay.
I added it.
So we're not,
Maybe it's behind the screen.
Oh, yes.
Sorry.
but we're not including any functions which evaluate to 0.
No, it's just for the way it works out, either it should be identically 0 or it should be strictly positive on the open interval, being just greater than or equal to 0 at the endpoint. Okay. That's how it works out. But if you want to approximate continuous functions, if something is small in this order relation, then it's small everywhere, right? It's just small for pointwise. Less than or equal to epsilon. Well, so you have the constant function. If it's less than or equal to the constant function, epsilon. Well, let's say we're talking about rational numbers, the real numbers. All the constants are there. So you have some constant equal to epsilon. So something is strictly less than So the point is that there's very, when you talk about approximations, there's very little to choose between saying less than or equal to epsilon, or there's less strictly less than epsilon. Okay? As long as epsilon is not zero, then it doesn't make any difference to remove the epsilon. So the reason I'm saying that is we want to approximate continuous functions, and normally we take the suit norm, which is less than or equal to, strictly less than or equal to at the endpoint. That's irrelevant as far as approximating. Okay? So, and the point is that well, there are two ways of proving the approximation. Let's not worry about the approximation of continuous functions as well. It is important to know that, that this cone is the same as this. Okay. And there should be hopefully with an elementary proof. Okay, which is not going to use the hand back.
I think I have an idea of the converse.
Yes, good. You have an idea.
Yeah, like we just consider like sort of like so like I like sort of like
Okay, let me just state the question a little more thoroughly. We have P of X is in Z of X. And whether you want to talk about Z of X or Q of X or R of X, it's not very good. And it's, P of, let's say P of T is strictly greater than zero. If zero is less than T is less than 1. Okay? And the question, does this imply P of X equals some of X to the of some coefficients of Aij X to the I 1 minus X to J. Okay. So I and J are greater than or equal to 0. That's the question. You were looking at that?
yeah.
Okay.
I was thinking, like all the polynomials which are like plus or minus 1 and then plus or minus x plus or minus x squared plus or minus x so on, like these kind of polynomials, you sort of see that the number of like sort of like negative signs that we have has to be less than the number of the plus signs, because otherwise when we evaluate it at 1 we get a negative. And so because there's less negative signs, you can basically just like group up negative ones or positive ones and then factorize so that it's like Pascal's work.
No.
And then if there is a number which isn't like a plus 1 or a minus 1, which is like just like a plus somewhere, I think essentially what ends up happening is because it's sort of like x squared is sort of like uniquely the polynomial which goes in the sphere of x squared. So if like you have like a minus, like let's say like minus 2x squared, there's no way to sort of like, I might be wrong about this, but somehow in some sense it's like if you try to like majorize negative x squared by like x, for example, the only like number in front of x which will actually be that you majorize it is exactly 2.
When you talk about integers, whether it's integers or rationals or reals, it shouldn't make any difference. Okay, well, what is the proof that and back through or vector space. Or our vector space. And the reason that I'm saying a vector space is that And it's an ordered vector space, okay? The order. What that means is you have a positive cones, which is posed under multiplying by the positive elements of the field. 2 plus times cone, that's 1/2. And if it's not any possible, oh, in the usual sense. I want this to be no hold. Present might be that it's posed under multiplying by z plus. It will come under multiplying by 1/2. 1/2 something might be in the group. You might put something in the group or something 1/2. Takes that with the positive cone 0, 2, 3. That generates everything. There's a hole. Find some benefit. Actually, I don't. This is not very scholarly. I don't know who came first. And back is for norm. It's very similar. Trying to for order units, so all one. Okay. That means that some positive multiple of one. That's true. Well, in either case here, okay. Because well, it's certainly true for the pointwise order. You take one constant length, the constant equal to 1, and multiply by something as big as you want, greater than anything. And with Pascal, actually, that's not quite clear, right? But, I'm going to apply it to apply it here. Okay, so apply it to this one as well. And there's a corollary. So the theorem is that if you have a subgroup, subvector space contains the order unit, contains 1. This line says if you have W contains in Z, number 1, and you look at the relative order, W plus equals W intersect. If you're the positive functional on W, as the linear functional, positive on positive elements. And then it extends to W extends to 1 and the conclusion of that is that in such a space, if phi is a function, if phi G is positive for all H phi, all positive for all positive functions phi. Or Q. Positive for all positive functions. By the way, that's not necessary. It's not, the conclusion is that there's G is positive. Okay. and then evaluating at 0, and that's 0. So this is something that's constant doesn't mean that. Doesn't mean that the positive. Well, of course, we want the 0. So, and it just happens that it's sufficient to know that G is, we want to prove that G is a combination of monomials, two monomials. And well, let's prove this is strictly positive when zero one. Well, it's not true. But if it's not, and it's not look at the extreme. Now maybe the possible now. Not to look at the extreme. For the extreme point. Extreme points are just going to be the point evaluation. And the reason you can see that is this is a ring. And it's easy to prove an extreme positive functional state. You know, there are lots of extreme points. So the extreme points are just the homomorphism. Anyway, last time I pointed out that Pascal the limit wasn't. I claimed that was really because you can multiply things. But that's not reasonable because you can back some of these and you have a product which is 0. Okay? And that doesn't happen for polynomials, so it's not. There's no way this model ring structure is something that you don't see from the Barron diagram. Look at it as it actually has a natural ring structure. Okay. So, and in the ordered ring, next easy exercise. Stage of functionals of one on one. Or just, and then x and 1 minus x. Your positive functional is equal to 1 on 1. It's got to be value on x has to be some number, some real number between 0 and 1. Okay. That means it's multiplicative. It's for every monomial, you just take that monomial and that number. Okay. That power and number x to that power. That's what your extreme point is. Okay, so how are we going to use this? Okay, so now we want to prove that from over somewhere from here. Better for someone who ran like 70 pounds. Oh, is it moving?
Maybe it's kind of. No.
On there, how many people are there?
2 others.
Okay. They're locals. Oh, usually if I watch something. Meeting. Lecture has been given by someone next door at the field institute. But it's not broadcast there. It's broadcast in John to the field of New York. Related to the work that I've done. So I probably ought to attend it. So, how do we apply the corollary? That sort of pulls the G belongs to so of course I have to say point implies implies that G is equal to the sum of numbers. I guess these are independent. So we have to okay, so what I want to do is look at the two polynomials, 1 and G, okay? That's two polynomials. I want to look at the by kind of two. So, 1 and G are probably independent, right? So I guess I could draw them in the plane in the rational thing. Here. They're not independent of themselves. Now, Q squared some vector space that by 1 some space of this two-dimensional system. And the order unit is going to be generated in this period of time by possibilities. Because if you take 10 by 1 or 100 times 1 greater than or equal to anything else in here. So anything in here is in here. In order to okay, so draw the positive cone. Now, if you just had a cone, by the way, every cone is going to look like this. It's not very good bound. You don't know the boundary is in or out, but otherwise it's going to look like this. Now, we're assuming that G is not positive. Right? That means it's certainly not in the interior. No, it might be on the boundary, and the boundary is positive. Okay, but I can even prove that's not possible. Okay, because no matter where it is not in the interior. There's some functional phi, such that phi positive functional phi, which is phi, positive, and not equal to 0. Phi of 1 is equal. Phi of 1 is equal to 1. Phi of t is equal to 0. Okay. It's two-dimensional vector space, and the null space. I think the null space is here. And non-zero, I mean, positive and non-zero, and positive x-axis. It's going to be positive and non-zero on the point. Even if, well, we don't care whether it's non-zero. As long as it's less than or equal to zero, enough less than equal to zero, but we're not. Okay? We can make it equal to zero. But then this is also why it's just defined positive functional state, like one or one, defined on the student. By trying to extend it to the whole. Okay. What is the, oh, by the way, I'm not, it's G. I have to, it's in positive point wise, but I don't know it's strictly positive on all functions. Because it might be 0 at 0. So suppose, so I have to handle some special cases. So let's suppose that G is strictly positive on the closed limit, okay? Strictly positive. What? So it's strictly positive on closed limit, okay? So that's all the extreme points. That says that strictly greater than 0. Strictly greater than 0 on all extreme points. Then it's strictly greater than 0 on every function. That follows from that. And by the way, we find survey that the actual choice too. This is that's why. Case one. And now, and so P of G is strictly positive. By positive function. All right, that's case one. But, and this is not a contradiction a priori, because a priori phi is just defined on the subspace. Phi of G is not strictly positive. It's not a contradiction. But as soon as you extend phi to the whole space, then it's a contradiction. Case one. So case one is not possible. You agree, Charlie? Case one says that every function is strictly positive. Here we have a function which is non-zero, it doesn't reach a state, and it's equal to 0. So when you find on this two-dimensional subspace, when you extend it, then it's contradicting this. Okay. So what that says, what does that say? What's the conclusion? It's what? Conclusion must be that G is in the form. Already in this, well, of course, to be in the two-dimensional surface, in the cone at all, it'll happen here. Yes. P of G. how many other cases are there? Well, it is positive, okay, so it is strictly positive in the interior. This is good. Page 2. Here, there is zero, okay. Knows what to do now. What happens to when all number vanishes to 0? Yeah, okay. And X is positive. Right? So divide out by what we get have let this go divide out by all of X. Then it's going to be strictly non-zero with X, strictly positive with X. So, okay, that's, but I guess I should say or G of 1. Okay. We have to do the same thing at 1. Right? So, sorry, that you? Yeah. Okay. You know, it's a bit dark in this room. Well, so that's why I then it's easy to go. I was just leading up to the subject about dark. Okay, so with G 1 is 0, what do we know? You might remind me of your name. You got it. Yes. Okay, good. Then, well, let's review first of all. If G is a polynomial of 0, then what can you say about it?
Power of X.
Yeah, yeah. So we've now divided out by that. Something if when we're finished, we get something in the sum like this, then multiply it back by power of X. Exactly the same for 1 minus. It's 0 at 1, and that means that's through some power of 1 minus. Divide that out, and you get something which is strictly positive. And therefore, it's strictly positive on every that's point extreme states that are homomorphism for point evaluations. That's an exercise. This is an ordered ring. We'll have what we take positive elements, two product of the natural product of two positive elements. Positive. We go. But, okay, with that, by the way, yeah, so we haven't even used inductor. So find out by X by some one over X and 1 minus X. Get something in case 1. Point. Therefore, by the corollary prime, it's positive. Then it'll be positive and multiply back by the power of the X. Positive. So that's the converse. That's true. Yes. We'll use, of course, field focus, precision focus. You have to reach for approximate single function for that. That means it's very quickly indicate. You have continuous function. Okay? So you approximate by polynomials. what we're pushing to the point, but the values of x. So you're using the interpolation problem. Did I erase the interpolation problem? But anyway, it's what one's downstairs, where you, for every point you close to the neighborhood, and we want it to be less than or equal to everybody. It's not that just at their hands. Okay? With every point you got a neighborhood or all the way over. So close to the neighborhood. But, less than or equal to everybody. Okay, when you do the same upstairs, you get a lot of polynomials upstairs, which get close at that point in the neighborhood. Not, everywhere otherwise. Okay, so these are your points upstairs, and here are your points downstairs. There's a polynomial in between. That's got to be closer than that. Oh, finite to many, you can compact this to the interval to get this finite to many. All right, okay, well, that's the house first number. Batch combination, order group. But oh, that's what a measure is. It's a linear function or a linear function. So define the translate. So what very quickly cover some I mentioned some other tricks. One thing you have to look at is index maps. There's in real case, real or complex case, even one of the index here, we go from 0 actually, in that case, it's very easy to write the map. But it's a little hard to prove exactly. Static algebra A to A over I. And I'm working on 4 at a time. I think we started at the New York City. Suppose you have a projection here, that is called B squared equals E to an 8 to 3. Then you look at E to the 2 started by 8. So E to the 2, that maps into 1. By example, I suppose therefore, it's in Q1 and Q1. That's the map. Complex number for the root minus 1. The fact that that picture exactly on the left and on the right. Look at the black here,